Hello, have a good day to you. I'm Ridhma Ganganath, and I'm one of the corresponding author of this research. For this successful research, I have Chaturu Rangana and Deepesh Jayasekar with me, and I highly appreciate their contribution toward this research. Sri Lanka is currently undergoing one of the worst economic crises in its post-independent history. Further, due to the prevailing forex crisis, the importation of goods has come to a halt except for a few essential items. Moreover, the prices of existing stocks of goods have skyrocketed, and students are compelled to work from home since the beginning of the COVID-19 pandemic. Considering the current circumstances, a low-cost closed-loop DC motor embedded control platform based on ARM for distance learning is proposed, where students can encounter hands-on virtual experience with their controlled design projects. DC motors are used for very large number of applications in almost all the industries such as manufacturing, automotive, medical applications, space application, as well as in robotics. As motion control is a key factor in the aforementioned applications, teaching a DC motor embedded control in the undergraduate curriculum is essential. In this paper, a low-cost ARM-based DC motor embedded control platform is presented so the students who are following control courses can implement their own prototype for an affordable cost using only few common components. The closed loop control algorithm is designed by using the PID controller, tuned the system using the classical trial and error method, and tested the system responses in real time according to different load conditions. The DC motor can be introduced as a common electromechanical component that can be used in any kind of motion application directly. It can constantly provide rotary motion, and also it can be applied to various applications by using specific coupling methods such as gear wheels or drums. The free body diagram with the electric circuit of the servo motor is shown in the figure here, and after applying Kirchhoff's voltage law, IA was defined as shown in the equation 1. Using the standard torque equation of the armature controlled DC motor and considering the excited flux as a constant, the torque equation was obtained as you can see in the equation number 2. Applying the Laplace transformation for both sides and got the omega equation as you can see in the equation number 3. Moreover, induced EMF in the armature is called back EMF, and according to Faraday's law of induction and considering the angular velocity, the back EMF equation can be obtained as you can see in the equation number 4. After deriving all the equations, the transfer function of DC motor was demonstrated like as you can see in the equation number 5. The main target of this research is to implement a low-cost motor controlling platform. Therefore, $30 was the maximum estimated budget to develop the hardware implementation so it is affordable to any student interested in building the prototype on their own. Only 5 main hardware components were used for this prototype. STM32 Discovery board was used as a control the location of the armature control DC motor by controlling the input voltage of the motor. As this motor control platform was implemented to test the control algorithms from basic to complex, a strong mechanical mates are needed to hold the components. Therefore, all the components were attached to 2.5 millimeter thick perspex board, where the motor was elevated from the board to put a varying load, and a shield made out of perspex was used to keep the STM32 board tight. In order to evaluate the open loop reaction of the DC motor for a given step input, the block diagram of the motor with its electrical and mechanical system was designed. Despite all the basic function of the DC motor, including the subsystem, a completed system block diagram was obtained as you can see in the figure above. PID controller is the most frequent controller design even in the industrial application due to its simplicity and flexibility. Moreover, when a plant has an uncloned mathematical model, PID can be useful, and we use classical trial and error method for the tuning process, and with this process the system can be lead to a steady state. The system was tuned using the PID gain as shown in the table above, and deploy the tuned controller into the microcontroller to execute the PWM signals throughout the DC motor drive. A 12-volt DC gear motor with the consist of an encoder was used to measure the position of the motor. Finally, a L298 dual H bridge motor driver allows the control of direction and position of the DC motor. These two graphs demonstrated the results of the system with no load condition. Disregarding the noise created in the control tick versus speed, it can be seen that the set speed and the current speed were the same, as the current speed error also lies in the zero. The results were obtained with the light load condition on the motor. Therefore, it is possible to see the error increasing the speed, deviating from the set speed until the system reaches the steady state. The controller still showed the underdamping characteristic, but the noise of the system was much higher compared to the no load condition. The load was further increased, and significant deviation of the current speed from the set speed was evident. Obtained error in the given time period was increased, but after a short time period, the current speed led back into steady state. The characteristic of the system has not changed, and this demonstrated the stability of the controller itself. The PID result demonstrate an underdamped system response throughout the three load conditions. According to the trials, responsible level of results can be seen over real time, and hence develop the system can be used for demonstration and implementations of model-based feedback control designs. For the further works, I would say we always wanted to share this motor driver controlling strategies, as this is a most crucial activity in the engineering world. For an example, in one of my individual research, we have used this feedback motor control design to our implemented inverted pendulum balance control design using the reaction wheel mechanism, as shown in the video below. With the previous experience regarding the noises, we improvised the theoretical approach to mitigate the measured noises. Then we used more advanced versions of motion control designed to implement the rotary inverter pendulum balance controller and get the steady state results. As you can see, there are a lot of things to learn about motor controlling, and it is always good to read about basic fundamentals regarding the motor controlling during the undergraduate period. Therefore, I hope this proposed low-cost test rig will be a great help to students who are doing control courses in our home country, Sri Lanka. Thank you.